Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tare, and I decided to do one more video in my series on group theory. Group theory is kind of incomplete, I think, without a discussion of Galois theory, because this was the beginning of group theory. And it's a little bit complicated, it's a little bit technical, but bear with me. I think you'll get it, and you'll see sort of the motivation behind how group theory got started. So let's begin. So Galois theory, like the name implies, was pioneered by this brilliant young French mathematician named Évariste Galois. He lived a very short life, unfortunately. I think it was 1811, 1832. I got the dates wrong, but he died at age 20. And he was, even though he was a math genius, like I said, he was a pioneer of group theory. He was pretty stupid about life, I think. I mean, the reason he died, he was a political activist. He was very politically active in France in the early 19th century. I guess this was shortly after the French Revolution. So there were a lot of political activists in France at that time. But he apparently got in a duel with someone he didn't agree with their political views, I guess. And he challenged this guy to a duel and he lost. They fought a sword fight and he got some very bad wounds and a couple days later he died from his wounds. Very sad, but also like I said, very stupid. And the interesting thing about this, there were kind of two major pioneers of group theory. There was Évariste Galois and there was another very famous mathematician, a Danish mathematician named Abel, Niels Abel. And he also died very young. He died at the age of 26, but his death was more because he had an incurable disease. He was also very poor, so he couldn't afford a good doctor. But he was the other pioneer of group theory. The name abelian group comes after him. So these two guys pioneered group theory. They both died very young, and that was kind of the beginning of group theory. And another thing I think I should mention about group theory, it started by trying to solve a very concrete problem involving polynomials. For a long time, I think probably ever since the beginning of math, mathematicians have been interested in trying to find roots to polynomials, like square roots, cube roots. But those are just a few examples. I mean, in general, you'd like to be able to solve for all the roots of a given polynomial. It turns out there's formulas for doing this for degree up to 4. I think you guys all know the quadratic formula that takes care of the degree 2 case. There's also cubic and quartic formulas. They're very complicated, but they were discovered, I believe, in the 15th and 16th century by a handful of Italian mathematicians. Some really great ones like Cardano and Ferrari, and I forget the other ones. But anyway, and then it turns out that Abel, I guess the thing Abel is famous for, he actually proved that in general you can't solve a degree 5 or higher polynomial in terms of radicals. And his proof involves group theory. That's how group theory got started. Group theory got started in an effort to try to find roots to higher degree polynomials. Beal proved it was impossible for degree 5 or higher. And similarly, Galois was interested in polynomials. And that was the beginning of what's known as Galois theory. So now I'm going to get into Galois theory. And like I said, it's kind of a complicated theory, but it involves the roots of polynomials. And before I go on, I think I should define what an irreducible and a reducible polynomial is. I'm sure you guys have all done factoring, polynomial factorization in high school. This is probably a very hard thing you had to learn. But it turns out an irreducible polynomial is just a polynomial. Imagine polynomials with integer coefficients. Those are the easiest to work with. And let's make a monic. So monic just means the leading coefficient is 1. So we say that a monic polynomial with integer coefficients is irreducible if you can't factor it into other monic polynomials of lower degree. That's what irreducible means. So it's kind of like prime numbers. Prime numbers can't be factored. Irreducible polynomials are a lot like prime numbers. Just think of them that way, except that instead of numbers, they're polynomials. That's how I like to think of them anyway. And a polynomial that's not irreducible is called reducible. So that's all reducible and irreducible means. And I think you guys are also familiar with a fundamental theorem of algebra, which says that over the complex numbers, every polynomial of degree n has exactly n roots, maybe with multiplicities. But it can be factored completely over the complex numbers. It means it splits into a bunch of linear factors. Kind of a neat result, I think. And if you're just dealing with irreducible polynomials, then it turns out that those roots are always distinct, I believe. And they form a group known as the Galois group. This is where Galois came up with this idea. So imagine you have any irreducible polynomial. Let's just call it P of x. Any monic irreducible polynomial with integer coefficients. So it has a general form I wrote on top. P of x is x to the n plus a sub n minus 1, x to the n minus 1, plus a sub n minus 2, x to the n minus 2, so on, plus a1x plus a0. These AKs are all integers. And that's a general, and we're assuming it's irreducible, that you can't factor it over the integers. So then, if that's true, I mean, even if it was reducible, you could still, by the fundamental theorem of algebra, factor it. And is x minus r1, x minus r2, so on up to x minus rn, where these rk's are the roots. But what makes it more interesting if it's irreducible is that then these roots all have algebraic degree n. I'm not even going to explain what that means right now, but they form a group. What's the most interesting thing about these roots. You can permute them. I mean, there's what's called the automorph. They form a field. Okay, if you take all these roots together and you would join them to the rational numbers, you get what's called an algebraic number field. You get an algebraic number field of degree r. And it turns out that, and we usually call that F, or sometimes people call it K. I'm calling it F here. So let's let F be the field of Q join R1, R2 up to Rn. Then you can do something kind of neat. You can permute the roots. It turns out that there are automorphisms, and I'm not going to get into this too much, but it turns out that there are certain operations you can do on this number field that take it to itself, such as it's a field, what's called a field automorphism, meaning it preserves multiplication. And it turns out the definition of the Galois group is just the automorphism group of the this field is called the splitting field, by the way. So it's the automorphism group of the splitting field of P of x. That is what we call the Galois group of the polynomial P of x. And we write it as gal of f. Sometimes we'll write gal of f comma q, or f over q, or aught f over q, because it's really an automorphism group. I know this seems like a lot. If you didn't understand everything I said, don't worry about it too much. But anyway, that's what the Galois group is. And I think it's better to look at some examples. So here's 4 examples. The first 3 are kind of trivial. So let's first consider the Galois group of the quadratic. The first 3 are quadratic polynomials, by the way, which are pretty easy to work with. So my first example is a polynomial P of x equals x squared minus 2. And that's very, very easy to factor. It's just x minus square root of 2 times x plus square root of 2, right? Because that's why they call them square roots. So remember that every number has 2 square roots, one positive, one negative. So 2 has the 2 square roots, the positive square root of 2, which we just usually write as root 2, radical 2. And it also has its negative, minus square root of 2. And it turns out you can permute those roots. So you get this field. If you want the splitting field of x squared minus 2, it's just the field q adjoins square root of 2. If you like, it's the set of all numbers, the form a plus b times the square root of 2, where a and b are arbitrary rational numbers. And it doesn't matter whether you adjoin square root of 2 or it's negative. I mean, you can map square root of 2 to its negative. That's a kind of interesting thing here. So you can start with a number a plus b square root of 2, and then you can map it to a minus b square root of 2. Obviously, those are different numbers if b is non-zero. These are what are known as conjugates, not complex conjugates, but they're called conjugate elements of q square root of 2. And so that is an automorphism. That's a non-trivial automorphism of this field. And it turns out it's the only one. There's actually only two automorphisms of q square root of 2. There's the one that doesn't do anything, and then there's the one that maps square root of 2 to minus square root of 2. So the Galois group of the polynomial x squared minus 2 is just this automorphism group which has order 2. So the order of the Galois group of the polynomial x squared minus 2 is 2. It's just, if you like, it's isomorphic to C2. C2 is a cyclic group of order 2. It turns out that's the only isomorphism class of groups of order 2, so it has to be C2. And the next two examples are also C2. I think it turns out that if you have any irreducible, any quadratic irreducible polynomial, its Galois group is going to be isomorphic to C2. But here's a couple other examples. So the second example is a lot like the first example. We have x squared plus 1. And I think you guys all know that minus 1 has exactly two roots as well. They're plus and minus I, square root of minus 1, if you like. So x squared plus 1 factors as x minus I times x plus I. So the Galois group in this case is going to, again, consist of two elements. One doesn't do anything. That's always the case. You always get an identity element of your Galois group, just like every group has an identity element. But that's not really interesting. The interesting element is the one that maps I to minus I. That's just complex conjugation. And that has a nice visual representation. I don't show it here, but if I was showing the Argon diagram or the complex plane, the complex conjugation just reflects the complex plane about the x-axis. So that's kind of a geometric interpretation of the Galois group of x squared plus 1. And again, it has two elements, and it's isomorphic to C2. I think example 3 is a little more interesting because it doesn't involve a simple square root. P of x equals x squared minus x minus 1. I think I meant to write plus 1 here. Yeah, I meant to write minus 1. And the roots of this polynomial are minus 1 plus or minus square root of 5 over 2. You might recognize, I think they're 1 plus, I might have messed up. The 1 plus or minus square root of 5 over 2. And I think you guys know that 1 plus square root of 5 over 2 has another name. It's called the golden ratio. So one of the roots is the golden ratio here. The other one is its conjugate, 1 minus square root of 5 over 2, which is really minus 1 over phi. So people usually write the golden ratio as phi, and that's one of the roots. The other root is minus 1 over phi. And again, this thing it has Galois group isomorphic to C2. The non-trivial automorphism in this case maps square root of 5 to its negative, minus square root of 5. Or if you like, it maps the golden ratio to its conjugate, which is minus 1 over phi. So that's the Galois group in this case, but it still has order 2. And I think the fourth example is the most complicated I give here. So this is a cubic polynomial. Like I said, every irreducible quadratic polynomial has Galois group isomorphic to C2. But cubic is where things get a little more interesting. It turns out that this polynomial x cubed minus 2 has Galois group of order 6. And its Galois group is isomorphic to S3, the symmetric group of order 3, or the symmetric group on 3 letters, which has order 6. I think I talked about that in a previous video. And it's a non-abelian group. That's another reason this is an interesting example. It doesn't commute. And it has two generators. I call them sigma and tau here. Sigma is the element that maps the square root of 2 to square root of 2 omega, where omega is a primitive cube root of unity. So omega, it turns out omega has algebraic degree 2. It's equal to -1 plus I times the square root of 3 over 2. It's one of the three vertices of an equilateral triangle, where the first vertex is on the positive x-axis, and the other two vertices have real component -1/2 and imaginary component plus or minus I square root of 3 over 2. So those form the vertices of a kind of a sideways equilateral triangle. And so you can imagine you have this one element of the Galois group of order 3 that just kind of rotates these roots. So we would send square root of 2, or cube root of 2 to cube root of 2 omega, which is a second vertex of the equilateral triangle. It would have been better if I showed pictures of this stuff, but you can kind of picture it in your mind, I think. And it also sends a square root of 2 times omega to square root of 2 times omega squared, which is the third. I can show it with my hand because it doesn't reach that far low, but it's square root of 2 omega squared, which is the third vertex of an equilateral triangle, and a max square root of, or cube root of 2 omega squared to cube root of 2. So it kind of rotates the equilateral triangle. That's one element of the Galois group, but it has another element as well. It has the element that maps omega to omega squared, and omega squared is really just a conjugate of omega. It's a complex conjugate in this case. So that's complex conjugation again. So you got two. I mean, this is a good thing because this is a geometric interpretation of the Galois group. One of the elements, one of these automorphisms, just rotates the roots 120 degrees, counter either clockwise. I mean, a generator rotated 120 degrees counterclockwise. If you square it, you get 120-degree clockwise rotation. If you cube it, you get the identity. And then the other generator is just complex conjugation. That sends omega to omega squared. And those two generators will generate S3. And if you want to think of this geometrically, it's just the symmetry group of an equilateral triangle. Sometimes people write this as D3, and that has 6 elements. It's generated by 120-degree rotation and reflection about the x-axis in this case. So anyway, that's the Galois group. I think I should say one more thing about this before I leave this slide. There's an important result known as the fundamental theorem of Galois theory. And what that says is that there's a one-to-one correspondence between elements or subgroups of the Galois group. The Galois group in this case is S3. That turns out to have 4 non-trivial subgroups, 6 subgroups altogether, if you include the group itself and the trivial subgroup that just has the identity element. So what are those subgroups? Well, one of them is generated by tau. That's the complex conjugation. That's just a subgroup of order 2. That subgroup is isomorphic to C2. But it also has 3 subgroups of order 3. There's a subgroup generated by sigma that's just going to rotate the equilateral triangle. Actually, I think I got it backwards. There's one subgroup of order 3. That's just the thing involving the rotations. But then there's 3 subgroups of order 2, and you can think of those as reflections. If you're thinking of D3 again, D3, that's the dihedral group acting on an equilateral triangle. That actually has 3 reflections. There's a reflection about every axis that passes through a vertex and the opposite, the center of the opposite side. There's 3 of those axes. So each of these subgroups of order 2 has one of those generators. So there's 3 subgroups of order 2 and 1 subgroup of order 3. And another thing you should notice is that the splitting field of the polynomial x cubed minus 2, which I said is the field where you have to join the cube root of 2 and omega, that also has 4 non-trivial subfields. And that's not an accident. It turns out that there's a one-to-one correspondence between every subfield of the splitting field of a polynomial and the subgroups of the Galois group. That's kind of a mouthful, but I have a couple slides on this. Here's a picture. I mean, let's say a picture's worth 1,000 words. So this picture actually illustrates what's going on with the fundamental theorem of Galois theory. This is exactly what I was just talking about. So the picture on the left shows all the subfields of the splitting field. They use zeta instead of omega here, but zeta is a primitive cube root of unity. Uh, and then they also have the cube root of 2. So your splitting field is the thing on top. Q join cube root of 2 and zeta. And then you've got this one subfield of order 2. That's Q adjoint, or of order 2, Q adjoint zeta. And then you've got 3 subfields of order 3, namely Q of cube root of 2 itself, Q of cube root of 2 times zeta, and Q of cube root of 2 times zeta squared. And then for each of these subfields, you have an associated subgroup of the Galois group. But notice they do everything upside down here. That's another thing about the fundamental theorem of Galois theory. You have to make the one of these graphs. These are graphs, by the way. You have to invert one of the graphs. So and the picture on the right, you've got all the subgroups of the Galois group, but here now you have the Galois group on the bottom. So the Galois group is S3, like I said. It's generated by these two things, which they call R and F. R is just the that's the thing that goes. That's A3. R generates A3. A3 is really just C3. It's the cyclic group of order 3. That's generated by the thing I was calling sigma earlier. Here they call it R. So R has order 3. It's just a 120-degree rotation. But then you got these other 3 subgroups of order 2, which are higher up in the picture. You've got one generated by F. Remember, F is really just complex conjugation. Then you got RF and R squared F. Those also have order 3, and those are the other 2 reflections. And then, on top you've got the identity. So those are the 4 non-trivial subgroups of the Galois group. And anyway, yeah. So in general, this holds. This is called the fundamental theorem of Galois theory. And here's another example. I think this example is a little less complicated, actually. So imagine your Galois group, your splitting field was Q adjoint square root of 2 and square root of 3. I mean, that would just be kind of the polynomial. You could get this from a irreducible quartic polynomial, x squared minus 2 times x squared minus 3. Uh, yeah, actually, that's not irreducible. That's irreducible. I guess you could start with x. You mean there's other irreducible polynomials that also give you this field. I'm not going to go into that, but and then you can look at all the subfields of this. It's pretty obvious that in this case there's 3 non-trivial subfields. Q adjoint square root of 3, Q adjoint square root of 2. Those are the 2 obvious ones. But you can also get Q adjoint square root of 6, because square root of 2 times square root of 3 is equal to square root of 6. So you have these 3 non-trivial subfields. They all have order 2 in this case. And then you also have a Galois group with generators, which they call F and G. F is kind of the thing that sends a square root of, I guess F would send square root of 3 to minus square root of 3. G sends square root of 2 to minus square root of 2. FG sends square root of 6 to minus square root of 6. And you can check for yourself that each of these things are subfields, and the entire Galois group, that's the thing on the bottom here, that's just the thing generated by F and G that has 4 elements, 1, F, G, and FG. This group is isomorphic to the Klein 4 group, which is the symmetry group of a rectangle. But anyway, that completes my talk on Galois theory. Oh, and there's one more thing I think I should show you before I finish. So you can calculate the Galois group of any irreducible polynomial you want. They get pretty complicated as the degrees get large, though. And it turns out for degree 3 is, I think, the first interesting case, because there's examples of irreducible polynomials that have Galois group S3. That's kind of the generic case. That was the case I just showed. Here they have a different example, x cubed minus x minus 1. that also has Galois group isomorphic to S3. But there are other irreducible cubic polynomials that have Galois group A3, or if you like, C3. They have order 3 rather than order 6. And example of that is x cubed minus 3x minus 1. So you get two interesting cases for degree 3. It turns out for an arbitrary degree, you can get any what's called a transitive subgroup of Sn. I'm not going to explain what those are, but there are examples of irreducible polynomials degree n whose Galois group is any transitive subgroup of Sn. And it turns out there's only one transitive subgroup of S2, that's S2 itself, or C2. So for a quadratic polynomial, there's only one possible kind of Galois group you can get. For degree 3, there's 2. For degree 4, I think it turns out there's 5. The numbers of transitive subgroups grows pretty fast. Anyway, they give a few examples. Yeah, they give an example of degree 4 here. This one happens to have Galois group A4. It turns out that the most common, for degree n, most Galois groups are the full Galois group, Sn. The ones that aren't Sn are kind of rare. But you can get, like I said, any transitive subgroup you want. In this case, x to the fourth plus 8x plus 12 has Galois group A4. That's the alternating group on 4 letters. X fifth minus x minus 1 is kind of a generic example. I guess I should have mentioned x fourth minus x minus 1. That's S4. That's kind of a generic example of order 4. And then you got, yeah, they have another example. It's also S5, x to the fifth minus 4x minus 1. But then they have an example with Galois group A5, alternating group on 5 letters. X to the fifth plus 20x plus 16. And I think I should mention one more thing before I get off this slide. And that is that the reason why, and this is what Abel discovered, the reason why, and you can also prove this with Galois theory, by the way. The reason why, in general, the degree 5 or higher polynomials are not solvable with radicals, you can't solve for the roots in terms of radicals, it has to do with the fact that the Galois groups in those cases are what are called unsolvable Galois groups. And it turns out that S5 and A5 are unsolvable groups. You have to go to degree 5 before you get to unsolvable groups. A5 is simple, by the way. And it turns out that every non-trivial simple group that's not a cyclic group of prime order, those are always unsolvable. So A5 is unsolvable. In general, AN is unsolvable for any n greater than or equal to 5. So if your Galois group is either SN or AN, that means that you can't solve for the roots in terms of radicals. Kind of neat. So anyway, that concludes my talk for tonight on Galois theory. I hope you enjoyed it. Thank you for watching. Long live math, and I'll see you guys next time. Bye.